Hey everyone, welcome to AirWise Academy, your trusted source for EASA Part 66 learning. We are now beginning a new and critical part of Module 2 Physics, Submodule 3 Thermodynamics. This is the science of heat, temperature, and energy transfer, principles that are at the very heart of engine operation, environmental control systems, and much more. To give you a clear overview, we have divided this submodule into two logical parts. In Part A, titled Temperature, we will build our foundation. We'll define core concepts like heat, temperature, and thermal expansion, and then we'll explore how we measure temperature, looking at both non-electric and advanced electrical temperature indicators. In Part B, titled Heat Transfer, we will expand on this foundation. We'll dive into the methods of heat transfer, conduction, convection, and radiation. We'll then study the fundamental thermodynamic and gas laws, see how they apply to engine cycles and efficiency, and even touch upon the principles of refrigeration. It is important to note that for this entire submodule, the required knowledge level for both B1 and B2 licenses is Level 2. So, let's begin with Part A. Our goal in Part A is to build a solid understanding of what heat and temperature are. We will begin by defining the core concepts: heat, its units of energy, temperature itself, and the important physical effects of thermal expansion and contraction. Then we will shift our focus to the practical side. How do we measure temperature in an aircraft? We will start with traditional non-electric temperature indicators before moving on to more modern and complex electrical systems. This includes a detailed look at electrical resistance thermometers, the ratiometer circuits used with them, and the widely used thermocouple temperature indicators. By the end of this session, you will have a comprehensive overview of the principles and instruments related to temperature. So, let's get started. Thermodynamics is the study of how heat interacts with other energy forms. Heat itself is energy, generated only when other energies convert into it. Think of it as the total kinetic energy of all molecules in a substance. We see this conversion in many ways. Mechanical energy from friction or compression turns into heat. Electrical energy does the same when current meets resistance, like in an iron or bulb. Chemical reactions release heat during burning or explosions. Radiant energy from light or X-rays heats objects on absorption. Nuclear fission in reactors or bombs unleashes massive heat, and ultimately, nearly all heat traces back to nuclear fusion in the sun. Now, let's connect heat to work and motion. When you compress a gas, you do work, and the gas warms because that work adds kinetic energy to its molecules. Let it expand under pressure, and it cools as internal energy is used. Friction works the same. Rubbing two surfaces demands mechanical work, and experiments prove the heat generated is directly proportional. At the atomic level, everything clicks. Molecules, atoms, and electrons never stop moving. In hot matter, they zip around with high kinetic energy. In cooler matter, less so. To slide one surface over another, you input work that becomes this molecular frenzy. So heat isn't mysterious. It's just the kinetic energy of matter's tiniest parts, transformed from the work we apply. Heat energy is measured in joules in the SI system, but two traditional units remain relevant: the calorie and the BTU. 1 calorie raises 1 gram of water by 1 degree Celsius. Note, this is distinct from the food calorie with a capital C. 1 BTU does the same for 1 pound of water by 1 degree Fahrenheit. In aviation, we rarely use calories or grams, but BTUs are standard when discussing engine efficiency or fuel energy content. To measure heat, we use a calorimeter. Burn a known weight of fuel, like 1 pound of aviation gasoline, inside it, absorb the heat in water, and calculate energy from the temperature rise. Experiments confirm a fixed link between heat and work. 1 BTU equals 778 foot-pounds. So, with 18,900 BTUs and 1 pound of avgas, that fuel holds the potential for over 14.7 million foot-pounds of mechanical work. Temperature is a key variable in fluid behavior, especially when gases change state. We use 4 scales: Celsius sets waters freezing at 0 degrees and boiling at 100 degrees, with 100 equal steps. Fahrenheit uses 32 degrees and 212 degrees, with 180 divisions. For absolute measurements, Kelvin starts at -273 degrees Celsius, absolute zero, and Rankine at -460 degrees Fahrenheit. Always confirm which scale you're using. Conversions are straightforward. Multiply Celsius by 1.8 and add 32 for Fahrenheit. Reverse it with subtract 32 and multiply by 5/9. Add 273 to Celsius for Kelvin or 460 to Fahrenheit for Rankine. These relationships are critical in technical work. Refer to the figure for a clear visual alignment. For gas law calculations using Fahrenheit, we convert to Rankine by adding 460 above zero or subtracting below. For example, 72 degrees F becomes 532 R, and -40 degrees F is 420 R. Remember, Rankine isn't interchangeable with Kelvin. It's just the absolute scale paired with Fahrenheit. In science and aviation manuals, you'll see Kelvin and Celsius as SI standards. But in the US, Fahrenheit remains common on instruments and in daily use. Throughout this module, expect both Fahrenheit and Celsius. The key? Always double-check the scale before plugging numbers into formulas or following maintenance procedures. Accuracy starts with the right temperature reference. Thermal expansion happens across all states of matter when temperature rises. Solids, liquids, and gases all expand, and nearly all contract when cooled. In solids, molecules are packed tightly and strongly attracted, so expansion is minimal compared to fluids. Liquids and gases expand much more. This is explored later with Boyle's law. But in aviation, we focus on solids because thermal changes directly affect aircraft metals and structures. Each material expands at a unique rate, measured as its coefficient of linear expansion, listed in this figure. To calculate expansion, use change in length equals coefficient times original length times temperature rise. This simple formula is essential for predicting material behavior under heat. Let's apply the formula. A 9-foot steel rod at 21 degrees Celsius is heated to 55 degrees Celsius, a 34-degree rise. Steel's coefficient is 11 times 10 to the minus 6. So, expansion equals 11 times 10 to the minus 6 times 9 times 34, giving 0.003366 feet, just 4/100ths of an inch. The rod grows to 9.003366 feet. That seems tiny, but if the rod is fixed and cannot expand, the thermal stress generates enormous force, enough to buckle metal or crack components. This is why thermal expansion is a critical design factor in airframes, engines, and every structural element. Engineers build in gaps, flexible joints, or select compatible materials to safely accommodate these temperature-driven changes. Temperature monitoring is essential for safe aircraft operation. We track engine oil, carburetor mixture, inlet and free air, cylinder heads, heater ducts, and turbine exhaust gas, among many others. Thermometers work by exploiting how materials change with heat, mainly through expansion or contraction. These changes are reliable and tied to each material's unique coefficient of expansion. The classic mercury and glass thermometer demonstrates this. Mercury expands with heat and rises in a calibrated tube to show temperature. However, despite its familiarity, the mercury thermometer has no place in aviation due to safety, durability, and precision requirements under flight conditions. The bimetallic thermometer is widely used in aviation. It consists of two bonded metal strips with different thermal expansion rates. One end is fixed, the other coiled, with a pointer on the coil. When heated, the metal that expands faster pushes the coil to uncoil, moving the pointer across the dial. On cooling, the reverse happens. The coil tightens, pulling the pointer back. This reliable mechanism powers direct reading outside air temperature, or OAT, gauges in light aircraft. A sensing probe extends through the windshield into the airstream, while the coiled strip and dial are mounted inside the cockpit for easy pilot reading. The Bourdon tube also serves as a non-electric temperature gauge in simple aircraft. It operates on vapor pressure. A sensing bulb filled with volatile liquid is placed where temperature is needed, like in engine oil. A long, narrow capillary tube connects it to the Bourdon tube in the instrument. As temperature rises, the liquid produces more vapor, increasing pressure. This uncoils the Bourdon tube and moves the pointer across a dial, calibrated in degrees, not pressure. When temperature drops, pressure falls, the tube recoils, and the pointer moves back. This rugged mechanical system is commonly used to monitor oil temperature, delivering reliable readings without electrical power. Electrical resistance thermometers are widely used in aircraft to monitor critical temperatures like carburetor air, oil, and outside air, especially in the -70 to 150 degrees range. The system includes a cockpit indicator, a sensing bulb made of special metal alloy, and connecting wires. The key principle: most metals increase in electrical resistance as temperature rises. Alloys with a high temperature resistance coefficient are chosen for sensitivity. The bulb is placed in the fluent or area being measured. As temperature changes, so does resistance. This signal travels to the cockpit, where the gauge reads directly in degrees Fahrenheit or Celsius, not ohms, giving pilots accurate, real-time temperature data. The electrical resistance thermometer looks like any standard temperature gauge in the cockpit, with dual versions available for multi-engine aircraft. Most are self-compensating, automatically adjusting for cockpit temperature variations. The sensing element is a precisely wound nickel manganese or alloy wire with a known resistance for every temperature in its range, embedded in insulation. This resistor is fully protected inside a closed-end metal tube, mounted on a threaded plug with a hexagonal head for secure installation. The winding ends are brazed to an electrical receptacle that accepts the connector plug prongs. The cockpit indicator houses a resistance measuring circuit, commonly a modified Wheatstone bridge. This circuit, shown in the figure, balances the unknown resistance of the temperature bulb, labeled D, against 3 equal known resistors, A, B, C, in a diamond configuration. A galvanometer connects across points X and Y. When the bulb's resistance matches the others due to temperature, the bridge is balanced. No voltage difference, no current flows through the galvanometer, and the pointer stays still. If temperature changes the bulb's resistance, the bridge unbalances, sending current through the galvanometer in one direction or the other. This moves the pointer, which is the galvanometer needle itself, across a dial, calibrated in degrees. A zero adjustment screw on the instrument face fine-tunes the pointer's spring tension at the balance point for accurate zeroing. The Ratiometer electrical resistance thermometer improves on the Wheatstone bridge system by eliminating errors from voltage fluctuations. It achieves higher accuracy and stability by measuring the ratio of currents in 2 circuit branches. The temperature sensing bulb is identical to the standard resistance type. Inside the cockpit indicator, a ratiometer uses 2 coils mounted on either side of a pivoting pointer assembly, all within the field of a large permanent magnet. As temperature changes the bulb's resistance, current splits unequally between the coils, creating magnetic fields that interact with the permanent magnet to rotate the pointer. The dial is calibrated directly in degrees. Let's see the figure for the internal layout. Here's how it works. The ratiometer has 2 current paths, one through the temperature-sensitive bulb and coil A, the other through a fixed resistor and coil B. A permanent magnet surrounds the assembly with magnetic flux denser at the top than the bottom. When the bulb resistance equals the fixed resistance, currents are equal. Both coils produce identical magnetic fields, torques cancel, and the pointer stays vertical. If temperature rises, bulb resistance increases, sending more current through coil A. This strengthens coil A's field, pulling it downward into the weaker lower flux. Simultaneously, less current flows through coil B, weakening its field and allowing it to shift upward into the stronger flux. The pointer pivots until a new magnetic balance is reached, directly corresponding to the new temperature. Ratiometer systems are widely used to measure engine oil, outside air, carburetor air, and other critical temperatures across many aircraft types, especially where accuracy matters or power supply varies significantly. You'll find them in multi-engine piston, turboprop, and jet aircraft. Their magnetic balance design ensures stable, precise readings even with fluctuating electrical input, making them ideal for demanding flight environments. When voltage stability or measurement precision is non-negotiable, the ratiometer is the preferred electrical resistance temperature solution.
Thermocouples are simple yet powerful temperature sensors used in aviation. They consist of two unlike metals joined at 2 points, a hot junction and a cold one. When the hot junction is heated above the cold, an electromotive force or voltage is produced in the circuit, directly proportional to the temperature difference. We measure this with a voltmeter connected across the cold junction, but the dial is calibrated in degrees Fahrenheit or Celsius for direct reading. The hotter the sensing junction gets, the stronger the voltage and the higher the indicated temperature. This reliable, rugged system is ideal for high-temperature applications. Thermocouples excel at high-temperature monitoring in aircraft engines. They're standard for cylinder head temperature in piston engines and exhaust gas temperature in turbines. Leads use specific alloys based on heat exposure, iron constantan or copper constantan for CHT, and chromo-alumo for the extreme heats of turbine EGT. The voltage generated is tiny, just millivolts, but directly tied to temperature. To maintain accuracy, thermocouple circuits have minimal resistance. You can't change wire material, length, or thickness without recalibrating, as it would skew the total resistance and readings. Proper wiring is critical for thermocouple accuracy. Every lead connecting back to the cockpit voltmeter must be the exact same metal as the thermocouple leg it's attached to. Copper to copper, constantan to constantan, and so on. This avoids creating unintended junctions that could generate false voltages and throw off readings. The cold junction is typically at the indicator, where compensation occurs. By keeping the circuit pure, we ensure the millivolt signal truly reflects the hot junction temperature, delivering reliable data for engine management. Thermocouple hot junctions come in specialized shapes for different engine needs. The gasket type forms a sealed ring of dissimilar metals, slipped under a spark plug or cylinder nut for secure contact. The bayonet type encases the junction in a perforated sheath, locking into a dedicated well on the cylinder head. In turbines, bayonets mount through the case directly into the hot gas path for inlet or outlet temps. For cylinder head temperature, always probe the engine's hottest cylinder, which differs by model, to capture peak conditions. The figure illustrates these designs and typical installations. The cold junction in a thermocouple system is housed inside the instrument case. Since the generated voltage reflects only the temperature difference between hot and cold junctions, cockpit temperature fluctuations would skew readings without compensation. This is handled by a bimetallic spring linked to the pointer mechanism, identical in principle to the bimetallic thermometer. It automatically adjusts the indication for ambient changes. A handy check: disconnect the leads and the gauge reads the panel's local temperature. For modern cockpits, digital LED numeric displays are increasingly common for clear CHT readouts. And that brings us to the end of this lesson for today. Now, let's warm up with a few questions to review what we've learned. Now, let's get started with question 1. Which of the following is a direct example of mechanical energy being converted into heat? A, an electric iron heating up when plugged in. B, a gas cooling down as it expands rapidly. C, a piece of metal becoming warm after being repeatedly struck with a hammer. The correct answer is C, a piece of metal becoming warm after being repeatedly struck with a hammer. As we mentioned earlier, mechanical energy can be converted into heat through methods like the impact of bodies. Hitting metal with a hammer is a clear example of this impact, where the mechanical energy of the moving hammer is transferred to the metal's molecules, increasing their kinetic energy, which we perceive as heat.
While option A involves electrical energy conversion and option B involves heat energy being expended, only option C demonstrates a direct conversion from mechanical energy to heat. Question 2. In aviation maintenance, the heat energy of fuel is often measured in British thermal units BTU. What is the definition of 1 BTU? A. The heat required to raise 1 gram of water by 1 degree Celsius. B. The heat required to raise 1 pound of water by 1 degree Fahrenheit. C. The mechanical energy equivalent to 778 foot-pounds of work. The correct answer is B. It is the amount of heat required to raise the temperature of 1 pound of water by 1 degree Fahrenheit. While the calorie mentioned in option A is defined using grams in Celsius, the BTU is the standard unit for heat energy in this context and is defined using pounds in Fahrenheit. Option C describes the mechanical energy equivalent of 1 BTU, which is an important conversion factor, but it is not the fundamental definition of the unit itself. As we learned in this lesson, 1 BTU is defined by its effect on a pound of water, making it the standard for discussions about engine efficiency and fuel heat content in aviation. Question 3. If the outside air temperature is given as 20 degrees Celsius, what is the equivalent temperature in degrees Fahrenheit? A. 36 degrees F. B. 68 degrees F. C. 88 degrees F. The correct answer is B. 68 degrees Fahrenheit. This is calculated using the standard conversion formula. Degrees Fahrenheit equals 1.8 times degrees Celsius plus 32. Plugging in our value, 1.8 multiplied by 20 gives us 36. Then, 36 plus 32 equals 68 degrees Fahrenheit. This conversion is crucial in aviation, as meteorological data and technical manuals may use different temperature scales, and accurate conversions are necessary for safe operations. Question 4. A 5-meter-long aluminum rod is subjected to a temperature increase of 50 degrees Celsius. If the coefficient of linear expansion for aluminum is 24 times 10 to the minus 6 per degree Celsius, what is the total expansion of the rod? A. 0.006 meters, B. 0.012 meters, C. 0.024 meters. We use the standard formula for linear expansion. Expansion equals the coefficient of expansion multiplied by the original length multiplied by the change in temperature. Substituting the given values, we have 24 times 10 to the minus 6 times 5 meters times 50 degrees. Multiplying 5 by 50 gives us 250. Now, 24 times 10 to the minus 6 multiplied by 250 equals 0.006 meters. Therefore, the rod expands by 0.006 meters, which is 6 millimeters. This demonstrates why engineers must account for thermal expansion in aircraft design, as even small expansions can create significant forces if the components are constrained. Question 5. What is the fundamental operating principle of a bimetallic thermometer used in aircraft? A. The uniform expansion of a single metal coil. B. The pressure change of a volatile liquid in a Bourdon tube. C. The differential expansion rates of two bonded dissimilar metals. The correct answer is C. A bimetallic thermometer operates based on the different rates of thermal expansion and contraction of two distinct metal strips that are bonded together. When the temperature changes, one metal expands or contracts more than the other. Because they are bonded, this difference forces the strip to bend or coil and uncoil. This mechanical movement is then used to drive a pointer across a calibrated dial indicating the temperature. This principle is different from a Bourdon tube gauge, which relies on fluid pressure, making option B incorrect. Question 6. In a vapor pressure Bourdon tube temperature gauge, what directly acts on the tube to cause a temperature reading? A. The expansion of a volatile liquid. B. The pressure of the vapor from a volatile liquid. C. The differential contraction of a bimetallic coil. The correct answer is B. This type of gauge uses a volatile liquid in a sealed system. When the temperature at the sensing bulb increases, the liquid vaporizes, creating more vapor and thus increasing the vapor pressure inside the system. This rising pressure is transmitted via a capillary tube to the Bourdon tube, causing it to straighten and move the pointer. The key is that it is the vapor pressure, not the liquid's expansion itself, that directly acts on the Bourdon tube mechanism. This distinguishes it from the mechanical action of a bimetallic strip, which is option C. Question 7. What fundamental property of a metal is utilized by an electrical resistance thermometer to measure temperature? A. Its ability to generate a small voltage when heated. B. The predictable change of its electrical resistance with temperature. C. Its physical expansion as temperature increases. The correct answer is B. This type of thermometer operates on the principle that the electrical resistance of a specific metal or alloy changes predictably as its temperature changes. Typically, resistance increases as the temperature rises. A sensing element or bulb made of such a material is placed in the area to be measured. As the temperature changes, so does the electrical resistance of this bulb. This change in resistance is then measured by an indicator in the cockpit, which is calibrated to display the corresponding temperature. This is different from a thermocouple, which generates voltage, or a bimetallic strip, which relies on physical expansion. Question 8. In a resistance thermometer system that uses a Wheatstone bridge circuit, what condition causes the galvanometer, which acts as the temperature pointer, to show a zero reading? A. When the circuit's voltage is at its maximum. B. When the bridge circuit is balanced and no current flows through the galvanometer. C. When the temperature bulb's resistance is at its highest value. The correct answer is B. The galvanometer, which is the instrument's pointer, measures current flow between 2 points in the bridge circuit. When the resistance of the temperature sensing bulb equals the known resistances in the bridge, the circuit is balanced. In this balanced state, there is no potential difference across the galvanometer, so no current flows through it. This results in a zero reading on the meter, which corresponds to a specific temperature on the dial. Any change in temperature unbalances the bridge by altering the bulb's resistance, causing current to flow through the galvanometer and moving the pointer to indicate the new temperature. In a ratiometer temperature indicator, what is the primary mechanism that moves the pointer to show a temperature change? A. The physical expansion of a coiled bimetallic strip. B. The balancing of magnetic torques from 2 coils in a non-uniform magnetic field. C. The pressure of a vaporized fluid acting on a Bourdon tube. The correct answer is B. The ratiometer operates on a unique electromagnetic principle. It uses 2 coils attached to a pointer, suspended in the magnetic field of a permanent magnet that is intentionally stronger at the top and weaker at the bottom. When the temperature changes, the resistance of the remote sensing bulb changes. This alters the ratio of current flowing through the 2 coils. Each coil then generates a magnetic field of a different strength. The stronger coil's field is pulled downward into the magnet's weaker region, while the weaker coil's field is pulled upward into the stronger region. This interaction creates opposing torques that rotate the pointer until a new balance is found. This balancing of magnetic forces in a non-uniform field is the core of its operation, making it highly accurate and resistant to voltage fluctuations, unlike a Wheatstone bridge design. Question 10. What is the fundamental principle that allows a thermocouple to measure temperature? A. A change in electrical resistance of a metal with temperature. B. The generation of a voltage when 2 dissimilar metals are heated at a junction. C. The magnetic field created by current flowing through 2 coils. The correct answer is B. A thermocouple operates on the thermoelectric effect. It consists of 2 different metals joined together at 2 points, forming a circuit. When one of these junctions, known as the hot junction, is heated to a higher temperature than the other, the cold junction, it generates a small electrical voltage or electromotive force. This voltage is directly proportional to the temperature difference between the 2 junctions. By measuring this voltage with a meter calibrated in degrees, the temperature at the hot junction can be accurately determined.
This principle is different from resistance thermometers, which rely on a change in resistance, or ratiometers, which measure current ratios. Question 11. In a thermocouple system used for cylinder head temperature, CHT, why is a bimetallic spring typically installed inside the indicator instrument? A. To generate the reference voltage for the circuit. B. To heat the cold junction to a standard temperature. C. To compensate for changes in cockpit temperature affecting the cold junction. The correct answer is C. The voltage produced by a thermocouple depends on the temperature difference between its hot and cold junctions. The cold junction is located inside the instrument in the cockpit where the temperature can vary. If the cockpit temperature changes, the cold junction temperature changes, which would cause an error in the temperature reading from the hot junction. The bimetallic spring automatically adjusts the instrument mechanism to account for these changes in the cold junction's temperature. As the cockpit temperature shifts, the spring expands or contracts, moving the pointer or adjusting the circuit to nullify the error, ensuring the displayed reading accurately reflects only the temperature at the hot junction. That's all for today's lesson. If you found this video helpful, please give it a thumbs up and consider subscribing to AirWise Academy for more aviation knowledge. We'd love to hear your thoughts or questions in the comments below. Turn on notifications so you won't miss our upcoming videos. Until next time, blue skies and happy learning.